Okay, this lecture is going to be on bilirubin metabolism. And to understand bilirubin metabolism, first thing we've got to understand is where does bilirubin come from? Well, the bone marrow produces red blood cells. Let me magnify this a little bit. Produces red blood cells through erythropoiesis. So when we get erythropoiesis to occur and we get red blood cell production, then it's going to occur. And so here we have erythropoiesis. That's going to form red blood cells. And in our bloodstream, red blood cells have hemoglobin in them. Red blood cells that have hemoglobin then, of course, and that hemoglobin is to carry oxygen to all the cells. Now, red blood cells only live for 120 days, and they die. What happens to those red blood cells when they die? Well, when the red blood cells die, they are disposed of in three areas, primarily the spleen, also the bone marrow, and then the liver. Those are the areas which are going to dispose of red blood cells when they die. The spleen is the primary area, however, and so therefore, magnify this up again where we can see this. So what's going to happen? These red blood cells die, and then they're going to go to the spleen. So we're going to go to the spleen. And in the spleen, what we're going to have happen is you're going to have cells that are called macrophages. These macrophages are part of your innate immune system, which is going to destroy these red blood cells or break them down and you reutilize products. So when we get red blood cells here, the red blood cells are going to be broken down into primarily two components. Going to be globin and heme, therefore hemoglobin. Globin is going to go back into the system so that it goes back over and will be utilized to form other red blood cells. Heme, however, is further broken down into iron, which also goes back into the system, and bilirubin. Okay? Now, bilirubin in this form is unconjugated bilirubin. And unconjugated bilirubin here, you will see, is lipid soluble. It is also toxic, and because of that fact, it gets into the bloodstream, unconjugated bilirubin, and it's going to go into the bloodstream because it is lipid soluble, not water soluble. Remember that's important. It is lipid soluble. Okay, it has to bind with something else, a protein, to be able to go through the bloodstream, since it is lipid soluble, not water soluble, and because it's toxic, it binds with albumin. All right, so now, if we look at that, then what we'll see is this unconjugated bilirubin that we have there, and then this is going to be our albumin it's going to combine with. And then what we will have to take place is we're going to have that is going to then go into the liver from the bloodstream, which is in the unconjugated form. So if I look at this situation, I'm going to have unconjugated, because it's going to come through the bloodstream, it's going to come back into the liver as unconjugated bilirubin. The liver also, because it has these things that are called Kupffer cells, they are also like macrophages, part of your innate immune system. Some of the blood is going to come directly from the bloodstream, those red blood cells, and they're going to be broken down by these Kupffer cells to form unconjugated bilirubin also. Okay. Now, I have this unconjugated bilirubin coming from those two sources. Now, unconjugated, again, being fat-soluble and not water-soluble, has to be turned into a water-soluble form to be able to be used. And this comes about by the liver taking glucuronic acid and combining it to make this now a conjugated bilirubin. Okay. Now, conjugated bilirubin is water-soluble. Now that it's water-soluble, it now can be excreted with the bile and therefore be able to be utilized by the body because now being in a water-soluble form. All right, so what we'll have then is we will have this situation where our unconjugated turns to conjugated. Conjugated then will be excreted with the bile and deposited into the duodenum, goes into the intestines through the ileum and into colon. Okay. Now, in the large bowel, we will have this conjugated bilirubin, as we talked about earlier. You'll have this conjugated form of this bilirubin in here. And this conjugated form, then, what you're going to see is this conjugated bilirubin will be attacked by bacteria. That bacteria, then, it's going to do is it's going to remove that glucuronic acid, so that what we'll have is we'll have this unconjugated form then will turn to conjugated form. When I remove the glucuronic acid, now is going to become an unconjugated bilirubin again. All right. So I've got this unconjugated bilirubin that has come because the bacteria then has attacked and removed the glucuronic acid. And because the glucuronic acid is removed, now I'm left with unconjugated bilirubin. Unconjugated bilirubin. Now realize that only about 10% of this conjugated bilirubin goes through this process of bacteria being converted to unconjugated. So I've got about 10% of that unconjugated now. Unconjugated then is going to be 5% of it is going to go back to the liver. Go back into that process, that's about 5%, and be recycled. The other 5% of this is going to go to the kidney and will be excreted in the urine. That bilirubin, unconjugated, that's excreted. Okay, so what you're going to have then is you're going to see this urine then is going to excrete bilirubin. And this bilirubin that comes out of the urine is going to be what's going to cause the yellow color to the urine. Okay, then what you will have happen then in the colon is this conjugated bilirubin, roughly the other 90% of it will be converted to a urobilinogen, which will give the feces its brown color, and that will make up about 90% of the conjugated bilirubin that was converted by the bacteria, 10% of it, and the other will be excreted in the feces. Now, this gives you a total overview of this whole process, and you should be able to understand what we've gone through here as far as the whole process. Let's run through it quickly, and that is the bone marrow is going to have erythropoiesis to occur. That forms red blood cells. Red blood cells will then go into the bloodstream. They'll live about 120 days. The red blood cells die. They are primarily broken down by the spleen, also by the liver and bone marrow. The spleen's the primary site. These have macrophages that break the red blood cells down into heme and globin. Globin will go into the system again and be reused to form other red blood cells. Heme will be broken down into bilirubin and iron. Iron will also go back into the system. The bilirubin that's formed at this point is unconjugated bilirubin and is fat soluble or lipid soluble, and therefore has to be bound with albumin in the blood to be able to be transported. It's also toxic. Once it gets to the liver, it's in the unconjugated state. The liver also has innate immune cells of Kupffer cells that are like macrophages, and some of the dead red blood cells are broken down by the liver to the same process, forming unconjugated bilirubin. The liver then takes all of this unconjugated bilirubin, combines it with glucuronic acid to now have it as a conjugated bilirubin, which is water soluble. That will then be excreted in the bile, which will go into the small intestines and go to the colon. In the colon, this conjugated form of bilirubin is 10% of it is broken down by bacteria. That takes away the glucuronic acid, making it an unconjugated form again. About 10% of it's there. 5% of that goes back to the liver and is recycled. The other 5% goes to the kidney, is excreted as bilirubin, and gives urine a giallo color. The other 90% of the conjugated bilirubin is converted to urobilinogen, which is excreted in the bile, giving the stool its brown color. Hopefully you understood all that. God bless you and thanks. All right, this lecture is on the continuation of the digestive tract. We're looking at the stomach, and in the lumen of the stomach, we're looking at the cellular makeup of the cells within the stomach and the things that they produce. There's many different types of cells, and as we look here, we'll see that we have these surface mucus cells along with these mucous neck cells that are responsible for producing the mucus, because remember, we're going to have hydrochloric acid in here, and that mucus buffer is the only thing that protects the cells from the hydrochloric acid damaging them. So we've got to have a good mucus content that's produced. You'll notice that we have our parietal cells here, and the parietal cells are going to be responsible for producing hydrochloric acid. We also have our endocrine cells that are made up primarily of two, and we will have a G cell that's going to be responsible for gastrin, and then we will have our D cells, which be responsible for somatostatin. Now, remember that when you see these cells, don't think that just because of this drawing that I'm going to show you afterwards, that these cells have to lay in any specific order that's laying there, so we can have them in different areas. But for simplicity's sake, I've put them all in a line so that you can see them to help clarify things. Also notice we'll have the chief cells. These chief cells are going to be responsible for producing pepsinogen, which the hydrochloric acid will then convert to pepsin. Okay, so now let's look at these cells, and what I've done here is we've just taken these cells and we're just going to simply go in and magnify this whole area. So if we just take these cells and go down and to magnify these in a large area and look at these cells individually, and that's what we're going to do now. So if we go up here and shrink this and get it out of the way, then we're going to see all of these cells that I have drawn out for you, and then we're going to look at their individual function. First of all, for clarification, you'll see that this is the stomach lumen, and then we'll have these cells. You have the mucus cells that we showed earlier. This is the parietal cell that's going to produce hydrochloric acid. Our G cells for producing gastrin, D cells for producing somatostatin, and then we'll have our chief cells for producing pepsinogen. All right, so if we look at those cells, for example, on our pepsinogen, when it is produced, it's going to go into the stomach lumen, and because we're going to have hydrochloric acid here, it's going to combine with that to form pepsin. And pepsin then is going to be used to digest proteins. Now, If we look at the parietal cells, within the parietal cell, we realize that what we're going to see is we have proton pump in our parietal cells. And in the parietal cell, what you will have to happen is that we're going to have hydrogen released, which is going to be acidic. This hydrogen is going to come from the fact that water inside of the cell combines with CO2 to form carbonic acid. Carbonic acid will give up this hydrogen and then form bicarb. This should be a normal chemical process that you should be very familiar with because it's used throughout the body. These hydrogen then, because of this proton pump, will pump out hydrogens in exchange for potassiums that will come into the cell. These potassiums then will turn and be pumped out again along with chloride, which this hydrogen side along with the chloride then will form hydrochloric acid. And there's where your hydrochloric acid is going to come from for digestion. Now, there's other sources for hydrochloric acid that are produced, but this is going to be the primary source. Is going to be from this proton pump. Now, if we look at other sources that are going to be involved in this, we realize that this proton pump is going to be the major source for producing the amount of hydrochloric acid that is going to come, and it is a plus. So it's a positive reaction for hydrochloric acid to get it out there. Other things that are going to be involved in doing that are going to be the enterochromaffin cells. Enterochromaffin cells will have an action upon them to cause them to produce histamine. This histamine will go over and have tied bindings to the H2 receptors. These H2 receptors will then also have a positive response in enhancing hydrochloric acid production. Okay? Okay, now the enterochromaffin cells not only produce the histamine stimulated on its own, but will also have other receptor sites that will stimulate it as well. For example, the G cells produce something that is called gastrin, and gastrin, being a hormone, is going to be released into the bloodstream. And then what we'll see was this gastrin, then it is going to come and attach to our G receptors that are on our parietal cell. These will also enhance HCl production. The gastrin also has another impact. It has a G receptor that is on the enterochromaffin cell. It in turn will stimulate histamine release, which will go to the H2 receptors and therefore enhance hydrochloric acid production. We have another situation that will occur that will enhance the production, and that is our old friend, the vagus nerve. And the vagus nerve that you see here is going to come down. The vagus nerve, of course, being parasympathetic, is going to have acetylcholine release because that's our neurotransmitter, if you'll remember from our study on neurology. Then acetylcholine ties in with these muscarinic receptors. This is a neurotransmitter. It will bind to the enterochromaffin cells. Those enterochromaffin cells then, enterochromaffin cells then will stimulate histamine release. That will again go to the H2 receptors to enhance the release of production of hydrochloric acid. Muscarinic receptors are also directly on the parietal cells, and you'll see those go down to this muscarinic. So I have a muscarinic receptor on the enterochromaffin, muscarinic receptor on the parietal cells. So I get a double effect, and the acetylcholine stimulates histamine release just like gastrin does, and also I have a receptor cell that will go in, and it's going to stimulate also a positive effect on increasing hydrochloric acid. Okay, now, if I look at these things, I realize that I have several things that are enhancing hydrochloric acid production. Primary thing is going to be my proton pump, which is pumping out hydrogen, exchanging it for potassium, potassium going out, taking chlorine with it, and I have hydrogen chloride produced. Then I have my gastrin cell, which is going to produce the gastrin, or it's a G cell producing gastrin. It's a hormone, goes in the bloodstream. Then it's secreted to attack to the G receptor site on the parietal cell, having a positive or increased production of hydrochloric acid. I also have a G receptor on my enterochromaffin cell that goes and stimulates production and release of histamine that is going to go to H2 and therefore cause that to increase or enhance hydrochloric acid production. My vagus nerve, releasing the neurotransmitter of acetylcholine, is going to come to my muscarinic receptor, which I have a muscarinic receptor on my parietal cell and one on my enterochromaffin cell, and it will stimulate a positive response. So I have those four things: acetylcholine, I have my histamine release, I have my gastrin release at my G receptors, and then I have my proton pump. So I have those things that are going to enhance hydrochloric acid production. Now, I also have to realize that because I have all these things to enhance hydrochloric acid production, I have to have some things that will hold things in check for me and balance so I don't have an excess production of hydrochloric acid. Okay, so that comes into play through, number one, is through the D cells that produce somatostatin. Now, somatostatin has its effect in that it is into the bloodstream. It has an effect on three things. It will inhibit my production. It ties up the gastrin so that it can't cause an increased production. It'll also tie up my G receptors so that it decreases my histamine release, and then it has a direct negative impact on the parietal cells themselves. So it'll get negative impact on gastrin, it'll have a negative impact on histamine, and a negative impact on the parietal cells. So therefore what it does is this somatostatin will have a negative impact on hydrochloric acid. In every regard here, okay? Now, so that's one thing that creates a negative impact or feedback for that. The other thing that takes place that causes a negative feedback is we have arachidonic acid that is converted by the COX enzyme to create prostaglandins E2 and prostaglandins I2. These prostaglandins then come to the PG receptors, these prostaglandin receptors that are on the parietal cells, and they have a negative feedback on hydrochloric acid as well. So these are negative feedbacks. So I have my somatostatin and my prostaglandins that create a negative feedback. One other thing that happens with the prostaglandins is realize that it also has an impact on the mucus cell. And what it does here is it causes them, the mucus cells, to increase production of mucus and increase production of bicarb. So what I get with this is I'll have a plus mucus and a plus increase in bicarb. Okay, so if I get an increase of those things that are occurring from the mucus cells stimulated by the prostaglandin, Now, if you look at those things, you can easily understand that if you have a person who has a situation where they've got peptic ulcers to occur, there's many things that you can utilize that will help treat that. For example, the number one thing that you could do is use some antacids. Antacids will simply come in and neutralize. These antacids will neutralize hydrochloric acid. Now, they're short term, they don't last long, and their effects are not really good. You're talking about Tums, Rolaids, those kinds of things. You also can attack things like using things that will attack H2 receptors. And these things would be drugs like cimetidine, Tagumet, Zantac, those types of things. And by doing so, you can have those drugs, this cimetidine, and they will tie up the H2 receptors and decrease the amount of production. These things are, because of the histamines, they don't have a long-lasting effect, and over a period of time, the system will become adjusted to it and override, so it doesn't work for long periods of time. The best thing to do is focus on tying up the proton pump, and those will be proton pump inhibitors. Those will be drugs like Prilosec, Nexium, those things. Okay, so they're proton pump inhibitors. And they are the best thing to use. Okay, the proton pump inhibitors are by far the better thing to use, and it will tie those things up and will stop any acid production, because all these other things really lead to enhancing the effects of the proton pump. And if I can inhibit the direct proton pump, then therefore I can get a much greater impact upon decreasing hydrochloric acid. One other thing you have to realize is one thing that creates these peptic ulcers is using drugs like NSAIDs. And because if I use an NSAID, which is a non-steroidal anti-inflammatory drug, okay? Those, not a very good A. Those drugs, what they're going to do is they are COX inhibitors. And so what they do is they'll inhibit or tie up COX, so therefore you don't get prostaglandin release. So think about it. If I don't get prostaglandin release, then I'm not going to have this negative impact on hydrochloric acid, so therefore I would get more hydrochloric acid produced. And I'll also have an impact so that I don't increase mucus and I don't increase bicarb. So I've compounded the problem. I have more hydrochloric acid produced, but I've got less mucus and less bicarb, which helps protect the hydrochloric acid in the stomach to start with. Okay, that should give you some clarification on those things that are produced within the stomach, and hope that helps. Thank you.